Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping, scientific discoveries that are revolutionizing our world and touching our lives. And in this hour, it's time for you to participate. It's time for you to get in on the fun. Okay, let's move right on to the next listener phone call.
This is Gloria, Pottstown, Pennsylvania, WEEU. I was wondering, with these black holes, why can they not rig up a probe and send it into the black hole with a camera? Pretty much like they have those on-man things with the Army, that they can take pictures, send it back, and then we can find out more of what is going on in the black hole. Thank you. Bye-bye.
Well, you ask an excellent question. First of all, we do exactly that to the planets and the moons. We take a camera, put it onto a rocket, and we actually send them into Jupiter and Saturn and different places around the solar system. And as a consequence, we know an awful lot about atmospheres, about the surface, about the structure of the planets because we have probes with cameras. However, when you talk about black holes, there's a catch. There's always a catch someplace. First of all, the nearest black hole is many light years away. For example, we have a raging a black hole at the center of the Milky Way galaxy. Tonight, if you go outside, look in the direction of Sagittarius. In that direction, there should be, by rights, a fireball. There should be a fireball there, which is the galactic nucleus, the center of the galaxy. You can't see this fireball because it's obscured by dust clouds, and the disk of the galaxy, yes, has lots of dust. In fact, that's where we come from. We are made out of galactic dust, but it's a nuisance if you want to see the center of the Milky Way galaxy. At the very center, there's a raging black hole. It weighs 2 million times the mass of the sun. So what's the problem? And the problem is these black holes are located hundreds, thousands of light years away, and each light year is about 6 trillion miles. So in other words, we're not going to go to any black hole anytime soon. They're simply too far because the universe is too big. Now, that doesn't prevent us from dreaming about sending a probe or a camera into a black hole. Now, the next best thing you can do is to get a computer to simulate Einstein's equations for a black hole. And we've done that. If you saw the movie Interstellar, starring Matthew McConaughey, they actually take a rocket and go through the gateway, the wormhole, to a black hole. And using computers and Einstein's equations, you can actually see what a hypothetical journey would look like. All sorts of bizarre things happen when you fall through the wormhole, connecting you to the black hole to perhaps maybe another universe. So if you see the movie Interstellar, it gives you the best computer rendition of traveling through a black hole because the nearest black hole is simply too far away, trillions upon trillions of light years, and we're not going to go that distance anytime soon. Okay, let's move on to the next listener phone call.
Hi, my name is Jen. My question was, how many monkeys have to evolve to create a whole other species?
Well, that number depends upon the circumstances and the species you're talking about. First of all, we have to even define what a species is and how we tell two species apart. And this is where biology starts to get a little bit of fuzzy, even in the definitions of species. Usually, biology books say that when two groups of organisms can no longer mate and produce viable progeny, that's when these two groups have separated, and they have speciated, and they're no longer part of one species. Okay? Now, there's lots of ambiguity. Okay? For example, what about the donkey and the mule? And what about the liger? The liger is a cross between a tiger and a lion. Believe it or not, you can mate a tiger and a lion and come out with a liger. So, how do you define two different species, given the fact that they can, in fact, mate and produce progeny? But these progenies are usually sterile. Therefore, you cannot create a third distinct species by mating two species, even though they are very close. Now, take a look at our own species, the Neanderthals, for example. Most people would say, and many biologists would say, that the Neanderthal is a separate species from humans. How come we know that? Because we can't mate with them. Well, that's been disproven. In fact, on our airwaves, I've actually interviewed the man who did it. The man who took Neanderthal skeletons, about 6 of them, and extracted usable DNA from the Neanderthals, and from that created a composite genome. That's incredible. A composite genome of the Neanderthal man. And the Neanderthals, do they constitute a new species, different from us? And the answer apparently is, well, we don't know. Maybe no, because according to the person I interviewed, he sequenced the genes and found there is about a 1% overlap. Incredible. A 1% overlap between our DNA and Neanderthal DNA. So in other words, our ancestors mated with them. This is rather shocking, because we used to think that Homo sapiens are all high and mighty and that we are unique and that we're at the top of the evolutionary chain, and we now realize that we share DNA with the Neanderthals. In fact, certain characteristics that we shared are very interesting. One of them is to withstand cold climates. It turns out that Neanderthal DNA might have been useful because the Neanderthals lived in iced areas of northern Europe much longer than we did, and they were better adapted to the Ice Age than Homo sapiens. Also, he said, certain characteristics may be traced to the Neanderthals. For example, red hair. There's indication, even though it's not conclusive yet, he said, there are indications that red hair is a byproduct of mating with the Neanderthal. And so to sum up, usually biology books say that you have to speciate when you can no longer mate with the other species. But then what about the Neanderthal? Okay, let's move right on to the next listener phone call.
I'm calling from Sterling, Massachusetts. My question is about the cosmic background radiation, which is due to the Big Bang. The background radiation is continuous, and the Big Bang was an explosion. So could you resolve that paradox? Thank you.
Okay, first let's define some terms. First of all, when you turn on your radio, you of course get static if you're between stations. Where does that static come from? Well, it turns out that a lot of it comes from Jupiter. Believe it or not, Jupiter is quite radioactive, quite energetic, and we now know that a fair amount of the static you pick up on radio comes from the planet Jupiter. What about the other pieces of static? Well, some of it comes from the Big Bang. Genesis, the origin of the universe. You're actually listening in on remnants, an aftershock, the afterglow of the creation of the universe itself. So how does that work? Well, as the gentleman pointed out, the Big Bang was just basically one gigantic fireball that erupted, and gradually over time it began to cool off and created the stars and the galaxies that we see around us. However, about 300,000 years after the Big Bang, there was a very important event that happened, and that is that atoms could form for the first time. You see, before 300,000 years ago, before the incident of the Big Bang, out to 300,000 years, it was too hot. The universe was too hot. The universe was opaque. You could not see very far if you were alive during that time. The universe was very opaque, and it was cool enough 300,000 years after the Big Bang for atoms to condense, for electrons to go around hydrogen. That point is the radiation picked up by our satellites. It's the radiation picked up by your radio. So your radio is picking up radiation 300,000 years after the instant of creation. And that resolves the problem. The gentleman asked the question, the cosmic background radiation is smooth, but the Big Bang was a violent event. How do you reconcile the two? Well, the Big Bang came first. It was that violent event which sent all the gaseous materials out into outer space, but it took time. It took time for that gaseous fireball to cool down, to the point where atoms can form. At that point, space becomes transparent. Now, we've always thought of empty space as being a description of the universe, but that's not always true. In the first 300,000 years of our infant universe life, the universe was basically opaque. You couldn't see very far. 300,000 years after the Big Bang, the first atoms began to condense. The familiar atoms, hydrogen and helium, lithium, began to condense out of the primordial gas that came out of the Big Bang. And that primordial radiation, 300,000 years after creation, as atoms were condensing, that is what you pick up when you look at the cosmic microwave background, which is the echo of the Big Bang. Not the Big Bang itself. It's the echo of the Big Bang 300,000 years after the instant of creation. Okay, well, let's move right along now to the next listener phone call.
Hi, this is Paula. I'm calling from Camdenton, Missouri, and I would like to ask, how long does it take for a stem cell and tissue to form an ear? How long does it take from start to finish to put together the ear or any other part? Thank you very much.
Okay, well, first of all, let me explain how we do it, and then I'll ask you a question of how long does it take. First of all, stem cell technology is very primitive, not that advanced, but not even using cells that are not stem cells, scientists at Wake Forest University have been able to create all sorts of human organs, not just the ear. At the present time, not even using stem cells, ordinary cells that have been treated specially, we can create carbon copies made out of plastic of ears, noses, cartilage, skin, blood vessels, heart valves, bladders, and windpipes. That is incredible. It's almost like walking through Frankenstein's laboratory. I had a chance to take a film crew from the Discovery Channel. We flew down to Wake Forest University in North Carolina, and we visited the laboratory of Anthony Ataya. Maybe you've seen some of his work on science specials, and you sort of feel like, well, feel like Frankenstein's doctor walking through the hallway at Wake Forest University, looking at jars containing human organs, human hearts, human livers. Kind of eerie. But then you realize that, well, these are mock-ups. These are practice attempts to create kidneys and livers and hearts. Because right now we can't do that. Right now we can basically create tissues made out of basically one type of tissue. However, the liver and other organs of the body require many different kinds of tissues, and that's where it takes time. Now, the caller asked, first of all, how long does it take to grow an organ? The answer is a few weeks. You can grow a whole ear in about 2 or 3 weeks in the laboratory. In fact, there's even the program that I hosted for the Discovery Channel called 2057, talking about the future, where we actually visit these laboratories and interact with the scientists who are, in fact, creating bodies of the future. Now, to create a clone of the brain, of course, takes a lot more effort, but it turns out that already with today's technology, we can already begin the process of creating organs that are almost indistinguishable from human skin, bone, cartilage, noses, ears, heart valves, and bladders, and even windpipes. Truly miraculous. Okay, let's move right along to the next listener phone call.
Hi, my name is Rick. I'm calling from Interstate 15 south of Las Vegas, driving a truck. My question is a neutron bomb a neutrino emitter, or does it create neutrinos? If so, if you have a neutrino detector and you are setting off a neutrino emitter, wouldn't you be able to detect things on the other side of whatever it is you're trying to look into, such as you suggested the Earth?
Well, first of all, let's talk about the neutron bomb, and then let's talk about neutrinos. First of all, the N of the neutron bomb does not mean neutrino. It means neutron. It is a neutron bomb, not a neutrino bomb. In fact, in physics, we use the neutrino bomb as a joke, because if a neutrino bomb goes off, what happens? Nothing. Absolutely nothing. Because your body is being penetrated by billions upon billions of neutrinos from the sun, black holes, and whatever, and you don't feel a thing. Neutrinos, in fact, can go through light years of lead and not even get absorbed. That's incredible. Think of our solar system made out of solid lead, and you can shoot a beam of neutrinos right through it. So a neutron bomb, the N stands for neutrons. They, in turn, can do a lot of damage. A lot of the damage from bombs actually comes from neutrons. So the N bomb, the neutron bomb, neutrons do cause a lot of damage. And so the neutrino is emitted as a byproduct of the fusion process, but the neutrinos are extremely ephemerate. That is, they go right through matter without hardly noticing it. And that means you can send it right through the center of the Earth. One day, perhaps we'll have neutrino detectors that can detect earthquakes on the other side of the Earth, because they go right through the Earth as if the Earth is made out of nothing. So neutrinos are quite different from neutrons. Okay, let's move right on to the next listener phone call.
It's Randy calling from Sebring, Florida. I've got the age-old question of which came first, the chicken or the egg. Have a good one.
Well, you ask a very interesting question. The answer, I think, is neither. That is, both the chicken and the egg evolved from a much more primitive form millions of years ago. First of all, if you look at the fossil record, you can begin to see that about 500 million years ago, we had the Cambrian explosion. Before then, before the Cambrian explosion, we had single-celled animals pretty much. After that, we had multi-celled animals of increasing complexity, including primitive backbones. And the question is, where does a chicken and egg fall into that evolutionary framework? We'll find out after the break. Let's take a short commercial break. And after the break, we're going to talk about what came first, the chicken or the egg. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. And before the break, we had that ancient question, which came first, the chicken or the egg? Well, if you go back into the fossil record, you can go back, for example, 200 million years ago, where we have the birth of the dinosaurs. But the dinosaurs, of course, laid eggs. In fact, we think the chicken, in some sense, is a dinosaur. Living dinosaurs are the birds, we think. Now, even going further back into the record, we have trilobites. Even going back further into the record, we eventually hit the Cambrian explosion 500 million years ago. And at that point, we begin to see, even before that, single-celled organisms. Now, single-celled organisms, of course, don't lay eggs. Single-celled organisms simply bifurcate, split in half. But some of them release spores. And these spores allow them to survive periods of famine, periods of intense heat or cold. And we think perhaps in the spore we see the possibility of eggs beginning to emerge. And so we begin to see that around that time, around half a billion years ago, 500 million years ago, the Cambrian explosion, all of a sudden we see the emergence of animals with primitive backbones, with structures like starfish, or the organisms like us with a single backbone. And around that time, spores eventually became eggs, and all of a sudden the fertilization process became bisexual. So around that time, we made the transition from single-celled organisms, we simply split, no chicken nor egg, those organisms simply split, to more complex modes of survival like spores, and eventually the chicken and the egg. So both of them evolved simultaneously. Okay, let's move right on to the next listener phone call.
My name is William, calling from Virginia. And my question is on spintronics and its possible applications to technology, and in particular quantum computing. Thank you.
Well, you ask a question that even the CIA is interested in, with all these leaks coming from the government. God, Washington, D.C. is like a sieve. Everyone's leaking documents left and right. How can you run a country if all your secrets are released? Well, one document was rather interesting. It was from the NSA, and it said that, yeah, they were looking at quantum computers. They didn't think there was anything there right now. But yes, the CIA, the NSA, and all the spy agencies are looking at quantum computers. So let me explain. We know that Moore's Law is the basis of American prosperity. That's why we have computers that double in power every 18 months. Moore's Law. But Moore's Law cannot go on forever. In the coming decades, for example, computer chips, your Pentium chip, will have layers not 20 atoms across, but 5 atoms across. Once you go down to the atomic level, you get leakage, you get heat creation, and silicon is unstable. Silicon cannot do its magic when it overheats, and if you have layers of silicon that are 5 atoms across. In other words, Moore's Law could collapse. In other words, Silicon Valley could become a rust belt. We have many rust belts in the past. Look at Pittsburgh, for example, and Pennsylvania. We have large areas of the United States where old technology was replaced by new technology, and that's a good thing. It's a bad thing if people lose their jobs, but it's a good thing if we can educate workers to then accommodate the new technology that is being adopted to replace the obsolete technology. Well, here's the question. What's going to replace the silicon computer? That is a multi-trillion-dollar question. The CIA looked at it. The NSA looked at it. I'm sure the Russians have looked at it. I'm sure the Chinese have looked at it. And the short answer is, we don't know. Now, once we get down to the atomic level, then some people say, obviously, we have to have atomic computers. But atomic and molecular computers don't exist yet. And that's where the quantum computer comes in, as was mentioned. All atoms spin. They're like a spinning top. And if you put them in a magnetic field, they all point in one direction, like up, for example. So imagine an array of spinning tops all aligned vertically. That is a magnetic substance. Then if you make a switch and some of them turn upside down, you've done a calculation. And after the break, we'll tell you why the CIA is so interested in quantum computers. Is the CIA suddenly interested in modern physics for the hell of it? No. Well, because of the fact that in the coming decade, we're going to see a slowdown in Moore's Law, it means that it could affect the economy. Will you upgrade your computer knowing that last year's model is just the same as this year's model? Are you going to buy a new computer knowing that computer power never changes? No. You're talking about the collapse of a multi-trillion-dollar industry. We have to go to the post-silicon era. So many possibilities have been looked at. Molecular computers, quantum computers, optical computers, DNA computers, protein computers, spintronics, quantum dot computers. But of them, none of them, I repeat, are ready for prime time. Silicon is very versatile, very easy to handle. It's like a miracle chemical, but it can't last forever. Just like we no longer use gears and levers to make computers, just like we don't use vacuum tubes to make computers, we use chips. But chip technology will eventually get exhausted. So what's going to replace it? Well, one possibility is quantum computers. And why is the Pentagon and the CIA so interested? Because quantum computers can perform calculations and break the code of any nation. I repeat, any nation's codes can be broken by the CIA once you have quantum computers. They're much more powerful than ordinary computers, but hey, they don't exist yet because atoms are fickle. The slightest disturbance will make these atoms in a magnetic field tumble and go into random configurations. In other words, the computer becomes useless. Now, what's the world's record for a quantum computer calculation? IBM set the record, and that record is 3 times 5 is 15. Ta-da! Now, children know that, but here's a homework problem. Take 5 atoms, go home, and with that, multiply 3 times 5 to get 15. Well, now you know how hard it is. It is really, really hard to manipulate individual atoms. The slightest vibration, a sneeze a mile away, would be enough to make what is called decoherence. where electrons and atoms fall into total disarray. That's the problem today. By the way, if you want to become a billionaire, if you want to have your name in stone just like Edison, then invent a quantum computer. That would change modern history. At the present time, no one can make a complex quantum computer. Okay, let's take the next listener phone call.
My name is Robert. Awesome show, and my question is, why is it that scientists who believe in evolution don't believe in God, since God could possibly be on this evolutionary scale with us?
Well, you actually asked two questions, and the first question is about scientists and God, and the third question is, can God be on an evolutionary scale? Well, we can actually answer some of your questions. The Pew Organization, for decades, has interviewed American people on all sorts of crazy questions, including, do you believe in God? And when they interviewed scientists, they found something interesting. Going back almost 100 years, going back many, many decades into the past, they found that the percent of scientists who go to church, not just believe in God, forget that, but go to church, is about 30%. Even with all the scientific marvels with astronomy and the space program and stuff like that, even though clergymen no longer look at the heavens to try to find where heaven or hell is located, about 30% of scientists are still religious. Because, of course, religion and science are not necessarily in opposition to each other. I like to quote from Galileo, who once said that the purpose of science is to determine how the heavens go. That's the purpose of science, to determine how the heavens go. And the purpose of religion is to determine how to go to heaven. So in other words, religion is about ethics. It's about how to lead the good life. It's about how to be a good Christian or whatever religion you happen to believe in. That's the purpose of religion. The purpose of science is to understand natural law, which is different from ethics. Now, as long as we keep these two apart, there's no problem. The problem occurs when people who are believers of natural law begin to pontificate about ethics, or when religious people begin to pontificate about natural law. That's where we have problems. Well, the second part of your question goes beyond the question of simply scientists and evolution and God. But can God be placed on an evolutionary scale? Well, I think most religious people would say no, that the accommodation of evolution, religion, and science is not to accommodate God in religion, because God is supposed to be the ultimate. God's supposed to be beyond evolution. God does not evolve because of, for example, survival of the fittest or evolutionary pressures placed on God. God has no evolutionary pressures. And so the resolution of the problem of religion and God is not that God is on a scale of evolution, because many people who would say, who believe in God, that diminishes God. The resolution, I think, is that there really are two domains. Now, what was Einstein's position on God? Einstein's position on God was there are two kinds of God, the personal God, the God of prayer, and the God of harmony, the God of elegance, beauty, and simplicity. That's the God. The second God is the God that Einstein believed in. Well, unfortunately, our time is up. Once again, you've been listening to Science Fantastic with Professor Michio Kaku.